Good morning. Sorry we've had to change the style of the lecture, but hopefully this will work just as well. In fact, it might even work better. So what we're going to do is you're going to see 6 short videos. Each of one will explain a little bit about the sinusoid, and then there'll be an exercise at the end. What I suggest you do is go through them one by one. There are spaces in the notes for you to be able to actually put your answers in. And then I'll explain the solutions to each of the questions that is posed. I'll try and be available online for the normal lecture slot if you've got any questions to ask, or you can post things to the forum afterwards. Also be quite interested to know what you think of this format. Does it work well? And maybe we'll do some more lectures like this later on. So start working through the videos, stop and go through at the end of each one and go through the exercises. And then, if you've got any questions, post them on the forum. Thank you. The aim of this lecture is to explain how the sinusoidal function actually functions, how it works, how we can process it, and how we can manipulate it. We're going to go through it in quite a lot of detail and quite slowly, mainly because it really is the key building block for all we're going to talk about over the next few weeks and after Christmas in the Signals and Systems course that you'll take after Christmas then. It really is the key function to understand how we can process signals, how we can build our signals, and how we describe them mathematically. So in this section, I'm going to talk about the sinusoid function. Now, I will have assumed that prior to this lecture, you've read the sinusoidal wave material that's been posted on Moodle. And so I will quickly review what we mean to describe a sinusoid in the time domain and in the frequency domain. And then we'll look at the idea of how you can use the complex exponential form to describe both sine and cosine waves. Now this is vitally important for the work we're then going to do to look at how we use those waves to describe the sorts of signals that we use in many of our communication systems. We'll also look at how the use of sine and cosine functions are central to the concept of bandwidth and how we consider how much bandwidth a signal that we want to represent is going to take up. So this is a plot of our first main sinusoidal function. Now you can see that the sinusoid here starts from a value of 0 at t equals 0, rises and then falls going through 0 again, and then goes through a similar cycle in the negative side. We typically define this area here as the period of the sinusoid, the time that it takes to repeat the function. And you can see that over any period t, our function is repeating. So this is the general equation. Despite the fact that we usually talk about a sinusoid, more regularly when we use it in a communication situation, we use the cosine function. And so here there are 3 main parts that I want you to look at: the voltage, or amplitude, the angular frequency, and the phase. So we describe our function, which in this case we're going to call v, although we could call it x, we could call it anything we particularly like, but we'll call it v, partially because we often think about a voltage in electronic engineering terms. And what we're defining here is that it is a function of t, in that it is time that is varying. And so that's what's changing in our function. And we then have the 3 elements that define our sinusoid, or our cosine function. Now, what is important about these is if we specify these 3 elements, v0, omega 0, and phi 0, then we will be able to recreate our sinusoid perfectly. So if you're given those 3 values, everyone should be drawing the same function here. We know that the cosine function generally moves between plus and minus 1. And what we have here is an element that varies in time. So this is going to determine how fast our function varies as a function of time. So that's the frequency, how fast we go through those cycles we saw in the previous element. The initial phase at the end is going to tell us about which position we start from. Are we shifting along? And in this, our voltage in this case, but our amplitude is going to tell us how high our signal goes and how low it goes. So if we normally have a cosine in its natural form going between plus and minus 1, our v of t now is going to go from between plus and minus v naught. So obviously at its maximum this will be 1, so it'll be plus v naught. At its minimum this element here will be minus 1, so this will be minus v naught. And so that's our basic function. As I say, we will usually use the cosine version of it, but exactly the same is true of the sine. So this is a cosine function here. As we said, it varies, it's periodic, with a period here that is t, and this is going to be related to 1 over the frequency. So t is the time it takes to go through one cycle, and 1 over the frequency, or 1 over time, we could say that f naught is 1 over t. Essentially, this frequency, which we usually give in with the units hertz, is sometimes also called cycles per second, because essentially this tells us how many times we go through one cycle in every second. Now omega is our angular frequency, and this is about the time that it takes our sine wave or our cosine wave to move one radian. So in this case, our relationship between omega, our angular frequency, and our frequency in hertz f here is just going to be 2 pi, because to go through one cycle is going through 2 pi radians, to go right round one cycle. And so often we need this conversion here to convert between angular frequency and Hertzian frequency. As we also talked about, we have v naught plus v naught is now our maximum, and minus v naught is now our minimum. Our amplitude has shifted from plus and minus 1 to plus and minus v naught by that amplitude factor at the front. And we're going to assume that our initial phase is equal to 0, and in this case, if you put 0 into the cosine function, you'll know you'll get 1. So we have a maximum at t equals 0. The sine wave follows many of the same conventions. Period is still t, plus and minus v naught is the same. The only difference is we now start from 0, as we know that sine of 0, so when t equals 0, we'll get sine of 0 is going to be 0. In the previous example, we had cos of 0, we know is equal to 1. Hence we start up here at this point here, whereas in this case we start down at 0 here. So those are our basic cosine and sine functions. So they're exactly the same, identical in every way, going through the same cycle, except we can see that there's a quarter of a cycle difference between the cosine and the sine wave. So if we wanted to convert between the two, we can use this equation here, essentially remembering that our cosine is a sine wave shifted by a quarter of a cycle. We know that one whole cycle is 2 pi radians, so half a cycle is going to be pi radians, a quarter of a cycle is going to be pi by 2. Our negative comes about because we have to shift the sine wave backwards against time. So to move it backward against time to get the cosine, we have to shift in this negative direction. So we're shifting the wave backwards against the time axis. So we have to shift it backwards in this direction by pi by 2. So we get this pi by 2 shift here. So that's the only difference between sine and cosine. And we can continue changing the phase. So this is a cosine. If we shift it backwards, then we're going to get plus pi by 2. If we shift it another quarter of a cycle, we'll get plus pi. Now what if we shifted another quarter of a cycle? Well, your first inclination might be to say, well, surely that's just going to be plus 3 pi by 2. But what we never try and do is go beyond pi. So when we continue to move forward, we will actually get minus pi by 2. So we try and only have this unit here going between plus and minus pi. Of course, you could keep moving it over and over again, but when you get something like cos omega naught t plus 20 pi, what's that actually telling us? Well, this is telling us that essentially it has been through 10 pi by 2 cycles. Well, we don't actually know the difference between any one of these cycles. They all look the same to us. So 10 times through the cycle essentially means absolutely nothing. We're back where we started from. So we only usually use this as between plus and minus pi. So I'll finish this short video with an exercise. First thing to do, sketch in the time domain. So you want a graph that has time against amplitude. We'll call it voltage in this instance. There should be a space in your notes for you to do this. And I'd like you to plot out this function that we have here.